In this video, I'll talk through the higher chemistry unit 2 topic of esters, fats and oils. And in this video, you should be able to recognise and describe esters from their names and structures, explain how esters, fats and oils are formed by condensation reactions, predict the products of hydrolysis reactions, and also describe physical properties and uses of esters, fats and oils. Esters are chemicals formed by the condensation reaction between carboxylic acids and alcohols. Carboxylic acid on the left has a carboxyl group, C double bond O OH, and an alcohol has a hydroxyl group, an OH group. In this video, you see R used to represent the rest of the molecule, the variable alkyl group. So there might be 4, 3, 2, 1 carbon coming off it. It's not important for how they react together. Condensation reaction happens when two molecules join together and eliminate a small molecule. It's usually water. It doesn't always have to be. When it comes to naming esters, they'll have ethyl-O8 within their name. Methyl propanoate and also ethyl butanoate would be examples of esters. When it comes to naming them, the first part of the name will come from the alcohol that was used, and the second part of the name comes from the carboxylic acid that was used. For the two examples at the top, we have methyl propanoate comes from methanol and propanoic acid, and ethyl butanoate would come from ethanol and butanoic acid. Comes to their structures, all of the esters will have an ester link, and that is a COO or a C double bond OH. And this forms when the carboxyl group of the acid reacts with the hydroxyl group of the alcohol. Here is it laid out. Again, the R groups are just showing carbons that aren't important at this point. We're going to take the oxygen and hydrogen from the carboxyl group and the hydrogen from the hydroxyl group. They're going to be removed to form water. And then we join the C double bond O with the O to get our ester link. C double bond O and an O. Esters have sweet smells and they're more volatile than carboxylic acids. Volatile means they easily evaporate, which is what helps the smell get into people's noses. They're typically used as flavourings and in perfumes. They can also be used as solvents to dissolve other chemicals. A little aside just about solutions. If a chemical dissolves in water, it's said to be soluble in water. If a chemical does not dissolve in water, it's said to be insoluble in water. Esters would be insoluble in water. You can get some information about solubilities on page 8 of the data booklet. Important words to do with solutions is that a solute is a substance that is being dissolved, a solvent is the substance that is doing the dissolving, and a solution is the mixture produced after dissolving. And this ties in quite nicely with the whole soluble, non-soluble, soluble, insoluble idea of esters and water. When making esters, a few different procedures that we can use. On the left hand side, we have the more basic, simplistic method, and the right hand side, a bit more complicated. In both cases, we'd be wanting to use something like a water bath to heat the reaction, as the reactants and products are flammable, don't want to catch it on fire. In both cases, we have a condenser. This cools down any gases and prevents them from escaping from the reaction. On the left hand side, that would be your wet paper towel. Not particularly fancy, no offence. And on the right hand side, you have a condenser which is plumbed in with water to cool out any exhaust gases. When the reaction has been successful, there will be a separate oily layer that you can kind of hopefully make out on my diagrams. And you'll also be able to detect the sweet, pleasant smell. When it comes to breaking apart the ester back into the acid and the alcohol, we use a hydrolysis reaction. So we're splitting up that ester link and we're reforming the original chemicals. Often done with water, but we can do it with other chemicals. Well, picking up an exam style question, we're asked about methyl cinnamate, which is made from cinnamic acid and methanol. We're shown the structure of the first chemical and we're asked to draw the structural formula of an ester. So they're telling us here it's an ester. We could also maybe work that out from the fact it's a carboxylic acid here. Methanol is an alcohol. Well, methanol has 1 carbon in it. And an ester needs a C double bond O. During the condensation reaction, we have to make our water. We're going to take the OH off of the carboxylic acid, the H off of the alcohol. We're going to join those two together. We're going to be given this structure. Ways of checking, we have our ester link. We have 1 carbon coming off of the right hand side from the alcohol, and we've copied the diagram of the cinnamic acid as well. That would pick up the marks for that one. Next question, we're given a quite complicated chemical. This is erythromycin, an antibiotic. We're told to remove its bitter taste. We're reacting it with chemical to make this new chemical at the bottom. Again, a very complicated looking chemical. What we're asked is, which type of chemical have we reacted our antibiotic with to get this new chemical? Now, what I've tried to do is I've taken the original chemical and I've kind of lined it up so you can hopefully see, well, this all looks quite common, quite the same. You'll hopefully see that the right hand side is our original chemical. Now, the new chemical that we've made, that is an ester. So I'm recognising we've got a new functional group formed by a reaction. Esters, as we've talked about before, esters are formed from alcohols and carboxylic acids. Our erythromycin is taking up the alcohol part, which means our left-hand side chemical must have been the carboxylic. So it's recognising we're making an ester. Esters are made from alcohols and acids. We already had the alcohol, so this new chemical that we've reacted with must have been the carboxylate. In this question, we're asked which of these uses is least likely for esters. Well, esters have pleasant fruity smells. That means they are likely to be used in perfumes and flavourings. They are good at dissolving chemicals. That would make it good solvents. With toothpaste being more minty generally, that's less likely to contain. In this next one, we're talked about a specific ester, ethyl benzoate. We're preparing it in an esterification reaction. We've got an alcohol and acid heated together. We've got sulfuric acid to catalyse it. Suitable method for heating. Because these are involving flammable materials, we do not want to use a Bunsen burner. We would want to use a water bath or a heated mantle. Water bath's my go-to one. Next one, we're talking about an esterification, joining together, eliminating a small molecule. That is what happens in a condensation reaction. Here we're making esters and we're asked about what functional groups are reacting together. Well, esters are formed from carboxylic acids and alcohols. Alcohols have a hydroxyl group. Carboxylic acids have carboxyl group. That gives A. In this one, we've got an structural formula and we're asked to figure out what its name would be. What I'd suggest doing first is identify where the ester link is. The carbon with no hydrogens will be the C double bond O, and that is came from the acid. So sketching it out, drawing it out can help get across the idea. We have the acid. On this side, we have the alcohol. When it comes to naming them, we should start with the alcohol side, which in this case is on the right hand side. There are 2 carbons, so that's going to make it ethyl at the beginning. And on the other side, we've got 4 carbons, which is going to make it butanoate. It's going to take a bit of time, a bit of practice to get so that you can start to visualize these and draw them out and kind of figure out how it all fits together. Something that's quite good to do, even from the early days of you learning this, is if you look at each side, you've got something that has 4 carbons, that's going to be but. It's something on the right hand side that has 2 carbons, it's going to be eth. So propanoate makes no sense because that's 3 carbons and 3 carbons, whereas here we've got a 4-2 split. So things like that can help kind of like narrow it down quite early days. Drawing them out is a big help as well. Sketching them out can help get to your answers as well. I would suggest that strongly. Next up, we're going to get to fats and oils. Now, these are naturally occurring esters. And one of the differences here is that they have 3 ester links within their structure. They're again made by a condensation reaction, but this time specifically between glycerol and fatty acids. They're still broken down by hydrolysis reactions, as with the other smaller esters. In terms of their uses, they're concentrated sources of energy, and they're also required to transport and store fat-soluble vitamins in the body. Key chemical to this is the glycerol. That's the alcohol that's used to make these. Its full systematic name, that is propane 1,2,3-triol. Propane because there's 3 carbons in the longest chain. 1,2,3-triol because each of the carbons has an hydroxyl OH group coming off of it. And each of these hydroxyl groups can react with a fatty acid. One of the exam style questions they could ask you is, what would be the ratio of glycerol molecules to fatty acid molecules when they react together? Well, glycerol is a triol. It has 3 OH groups. So 1 glycerol can react with 3 fatty acids. So glycerol to fatty acid would be 1:3. If it was asking you about fatty acid to glycerol, it would be 3:1. That's how we get the answer there. What are fatty acids? Well, fatty acids are long-chained carboxylic acids, and they will often be shown in what's called skeletal form. One example would be stearic acid, and here it's drawn in skeletal form, and it's where each of the corners is a carbon. This one is C18H36O2, could be written as C17H35CH, where in the first set we're squishing everything together, and the other one we're keeping the group. Another fatty acid would be something like oleic acid. That has a carbon-to-carbon double bond within its chain, so this time it's C18H34O2 or C17H33COH. It's important to be able to tell if it's got double bonds between carbons or not. If you have the molecular formula where everything's shrunk down, a saturated fatty acid will have single bonds between the carbons, will have CnH2nO2. Every time you add a carbon-to-carbon double bond, you'll have 2 less hydrogens than the original molecule. So if you have this one here, C18H36, the number of hydrogens is double the number of carbons, therefore it will be a saturated molecule. And here we've got 1 carbon-to-carbon double bond, so we've lost 2 H's. The next one we've got 2 carbon-to-carbon double bonds. Yeah. Words that are used often here would be mono, unsaturated means 1 carbon-to-carbon double bond, whereas poly, unsaturated more than 1, 2, 3, 4, depending on the chemical. To be able to tell that in a lab, what you can do is you can react the chemicals with iodine or bromine. When reacting with the iodine bromine, the halogen, it will break the carbon-to-carbon double bond in an addition reaction. The more carbon-to-carbon double bonds you have, the more halogen solution that will react. And unsaturation is important when trying to explain the melting and boiling points of fats and oils. Oils will tend to be more unsaturated. This means they have more carbon-to-carbon double bonds. Those carbon-to-carbon double bonds prevent the molecules from packing closely together. And this means that there's going to be weaker intermolecular forces. It's going to be a lower melting point and more likely to be a liquid. So more carbon-to-carbon double bonds, less closely packing, more liquid. Less carbon-to-carbon double bonds, more closely packing. That's going to make it solid. Not too sure how well this little diagram comes out, but what I'm trying to show is at the top, we have no carbon-to-carbon double bonds. That allows them to pack nicely, tightly together, increasing the attractions between them. Whereas on the bottom part, we've got double bonds in all of our molecules, and this kinks them, makes it more difficult for it to sit closely together, and that's going to result in having weaker forces of attraction, then it's likely to be more liquid. In this question, we're asked to decide from the formula which one's the most unsaturated. What I would do here to make my life easier is I would bring all the carbons together and all the hydrogens together. So here we have our molecular formulas. Now within these molecules, so we have 2 different numbers of carbons to deal with. If there was 16 carbons, if it's saturated, so no carbon-to-carbon double bonds, you would have 32 H's, just double 16. If there's 18 carbons, you would have 36 hydrogens. This means that B and D are both going to be saturated substances. Next thing what I'm looking for is how far away from saturation are we? So A has 30 hydrogens instead of 32. That must have 1 carbon-to-carbon double bond, because every double bond reduces the H's by 2. Whereas the C18H32 must have 2 carbon-to-carbon double bonds because it's 4 hydrogens away from being filled up. In this question, we're asked to identify which one's the most saturated. This one's a little bit different because we're dealing with the fat or oil in this case. So the molecular formula is probably a little bit more difficult. What I would look at though is the melting points and boiling points. If it's most unsaturated, it's got the most carbon-to-carbon double bonds. That means we're looking at the bottom example. They pack less closely together, weaker intermolecular forces, more likely to be liquid. That's going to be a lower melting point, which means our third chemical, glycerol trilinoleate, is going to be our correct answer. In this question, we're told information about 2 different types of oil, and we're asked to explain the differences in melting points between them. We're asked about coconut oil having a higher melting point. So it's going to be more saturated. This means that the molecules can pack more closely together, and this results in stronger intermolecular forces. This is one of those cases where anything with a higher melting point has to have stronger intermolecular forces. That's almost a given in any type of question to do with melting points and boiling points. And it's fats and oils, it's to do with the packing. So closer packing, stronger forces, more carbon-to-carbon single bonds and double bonds, that kind of idea. Help pick up the marks for those ones. That brings us to the end of the esters, fats, and oils topic. Hopefully you're now more confident how to recognise and describe esters from their names and structures, be able to talk about condensation and hydrolysis reactions, and also look at differences in physical properties and the uses of esters, fats, and oils. Thanks for watching. Goodbye.